Thank you for coming to GTC DC and spending your time with us. Especially thank you for coming to my session. So, like I was introduced, I work with industrial customers, especially industrial ecosystem and manufacturings that are looking to apply vision AI technology to a very well-established industry. And that has now moved into vision AI agents. So let's start by defining what is an agent. We look at an agent as something that can perceive vision, sensors, time series data, etc. It takes that data alongside contextual knowledge with a set of models and does some level of reasoning or thinking. If you guys heard about Jensen's keynote yesterday, right? The ability that his models now think before they're answered. They're not just providing a data or a response. And then they're able to plan or activate, or provide an action. That might be to tell an operator what is wrong with the machine, how to clear an error. That might give you some insights into a quality process, or you might go tell a robot where a particular item is there to be able to be packed into such as a warehouse and logistics scenario. So these agents can be applied to a $50 trillion heavy industries, right? Anything from automation, AMRs, AGB, robotics, warehouse logistics, factory floor operation, facilities management. It's a multimodal problem. There's probably not a lot of places that have many different types of data as there is on the factory floor. And a lot of places where efficiency, productivity, throughput is just very, very important. So applying agentic AI to this industry to address challenges such as the labor, right? That's one of the biggest things. There is a lot of great operators that are now leaving that workforce. So we want to make sure we're capturing that tribal knowledge so that can be disseminated to new operations. Labor shortage is a huge thing that impacts everybody. Both the ability to work longer hours, but more efficiently, labor happiness, all of that. And then also the rising training cost of what it goes into uplifting the workforce, right? So we're making very complex things. One of the very complex things we make is even our own hardware, right? AI infrastructure. That is driving significant build and manufacturing. A lot of that was covered in Jensen's keynote. Those are very, very complex systems that require a lot of skills. So the ability of how do we help agents to help operators be more efficient, to help facilities and manufacturing be more efficient. So what could those agents look like? It can be a set of different models, such as traditional computer vision and tracking models, vision language models, or VLMs. Can be LLMs that can take in images and data, sensors, documentation, right? Manuals of how your machines work, or processes of your operations, how that works, third-party applications, and it does what I just talked about before. It looks at all that data, it looks at what's being requested, what is being tasked to do, it reasons, and then it achieves or executes a plan of action. That could be to help with failure analysis or giving real-time process insights as to what's happening on the factory floor, summarizing what's going on, summarizing what was done by a machine, what was done by an operator, what was done by a whole production line, provide alerts or even just information retrieval, right? Everybody's seeing those very large manufacturing dashboards that still require interpretation. That's a lot of numbers. But the ability to interact with your manufacturing data, your information, your facilities data in a human language format through agentic AI is one of the other benefits of this as well. So throughout this presentation, I'm going to go through some of the enabling technology from NVIDIA that is utilized to build these industrial AI agents or vision AI agents that are applied to manufacturing and industrial, how it kind of comes together, the benefits of those individual technologies, and then we'll go through some of the great solutions that our partners are bringing to the market, some success stories of how this can be applied, and hopefully that will give you, if you're looking for an end solution, some of the partners in our ecosystem go talk to. If you're looking to develop or take advantage of the technology yourself, you have a good place to start. So I'll play a quick video just to kind of give you a sort of a art of the possible of what I'm talking about when we're talking about visual agents. So now with the ability to look at an open space, identify, still do your computer vision, but do an overview or key findings, right? Safety harnesses, environment, worker protection. What's the ability? Ability to look at a facility, track objects, assets, understand if there's any hazards, right? One of the biggest issues with computer vision is the data that's required. The ability to do fleet management of robots. In this case, why is my robot not getting where it needs to go? Safety, security, hazards. In this case, the ability to understand a 3D space. Create a co-pilot for a forklift driver that tells it where that pallet is the most efficient use of that facility and then where to go. He doesn't have to figure that on his own. Vision AI agents can help with that and supply efficiency. Optical inspection, right? The ability to zero shot, not only get a yes, good, no, bad, but also insights as to what's possibly the nature of that defect, what possibly could have arrived at. Be able to follow a standard operating procedure with humans in the loops or robots in the loop that can intersect an error before it's actually executed, telling that operator, hey, you missed a step, you might have done something a little bit different. So those are a little bit all examples of AI agents. And then some of the benefits, right? The biggest benefit is looking at that labor and workforce challenge is how can I create agents that make my operators more efficient, that make my onboarding and training more efficient, and ultimately that makes my quality go up, my quality goes up, my margin goes up, my throughput through the warehouse goes up. Quality inspection, insights into processes, optimization, right? Everybody talks about a smart factory, but what you really want is a constantly improving, self-improving factory that's able to just do a feedback loop, right? That AI flywheel. Process change, you build new products, everything else. And so you want those agents, those insights into the process as it moves to help you create that self-improving factory. Safety and security, predictive maintenance, right? Downtime is a huge issue. Can I take an agent that's giving me a remaining useful life using different modalities? So where we are, and I think where most everybody, if they think about vision AI in manufacturing, they think about visual inspection. That was the first kind of applicable ones like AlexNet and the ability to identify a picture of a cat came around. That came about. So I would say that's fairly well ingrained and level of adoption. We're starting to see assistance agents or multimodal assistance agents start coming up. Things like following SOP, but also understanding the factory, understanding the nature of what's happening, right? I can get a sensor that tells me my machine has an alert, and I can get when that machine came back up, and that could have been 25 minutes. I don't know why that was 25 minutes. But if I look at a facilities camera, I can find out, wow, it took somebody 10 minutes to get to the machine before they started working on the problem, or they weren't able to get parts, or any number of things. So additional insights, agents. And then all of a sudden, when we have these agents that are helping our operators, every different persona through the factory, then we can start bringing them together and start creating optimization agents that are now giving you feedback. Instead of just giving you intelligence, they're actually giving you feedback as to how to make your processes better, that self-improving factory that we're talking about. All of this, our agents are put together or created in what we call the three computers, right? You need to simulate. One of the biggest issues with vision AI in manufacturing or manufacturing as a whole is the need for lots of data. Manufacturing is very bespoke, right? Unlike, let's say, smart spaces, I can take a people detection model and I can build a product for a stadium that tells me which bathroom has the shortest line or where the vending is the shortest line. I can build something for an airport. I can build something for a mall. That same model applies across the board. It's not the same thing with factory. Nobody's making the same things. Nobody makes things the same way. Everybody uses different parts. And you need that accuracy to be really, really high. So collecting that data, gathering that data is very costly. So that's where simulation and synthetic data generation can come in. The ability to take 5 images of defects and create a data set of 10,000 images of those defects to drive that accuracy. Being able to give variance in the way the light, the distribution of those errors or defects can really help, and now you're able to do that with simulation synthetic data. The main connection to the digital twins is through this computer, the ability to have virtual sensors that can feed, gather data from a simulated environment, use that to train the vision AI agents, and then eventually you swap that out from that digital twin camera sensor to the real sensor in your factory. Once you have that data, then you need your training computer that's going to train your AI agent brains, whether that be fine-tuning the VLM, CNN, VIT, VFM kind of pipelines, right? And that's going to happen. And then finally, you have your runtime. And the runtime is once you have those agents, where are they going to run? Some of them are going to run on the far edge using Jetson. Some of them may be running on the cloud. It's likely to be a distributed deployment most of the time. So NVIDIA Metropolis, so the team that I work with, we provide tools within each of these spaces, within each of these computers. So we have models to begin with, both vision foundation models and VLMs. We'll talk about those in a little bit. And TAO, or Training Adaptation and Optimization Toolkit, to help you train and adapt those models to your manufacturing environment. For simulation, we work with Omniverse. We have the Cosmos World Foundation models that can take synthetic data create synthetic data generation for you. And then when you execute that runtime computer, we have things like Blueprint with our video search and summarization, which the previous video that you saw, all those examples were based off of that Blueprint. We have DeepStream, which is the fastest way to do vision inference using our technology. It ensures that you're going to be able to meet those real-time, machine time requirements, ensure that you're getting the most bang for your buck, the most speed through your GPUs. And then we have NIMs to help deploy some of these larger generative AI models. So one of the things that is, kind of taking manufacturing vision AI agents leaps forward from that CNN sort of AlexNet, ResNet, YOLO, to the next step where we can do inline SOP monitoring, where we can start creating agents that can provide significant feedback, is the ability to look at video, but video with reasoning. And what does reasoning means? It means you have that chain of thought. So in this case, we're asking if somebody's taken a package and removes it without permission, right? You can give that to a non-reasoning VLM, like VLO 1.5, and it shows the response is it shows a video approaching a residential porch, picking it up, walking away. It didn't reason through whether it was allowed or not allowed, right? And that could actually been the person that the package was meant for, and you wouldn't know. Now you add reasoning, and then you see the chain of thought, right? He checks if anybody's watching, cautious of behavior checking his surroundings, suspicious because he's being a little too careful in the way he's picking it up and moving, and then you arrive at an answer that determines, that reasoned its way to say, yeah, this is more than likely a person that should not, that's stealing or taking that package without permission. Our reasoning VLM is Cosmos Reason. Just passed 1.5 million downloads on Hugging Face. Open source, the ability to be fine-tuned. It is compact at 7 billion parameters. And it reasons through prior knowledge, right? It's bounded in physics, which is very much needed for manufacturing and understanding, for that understanding of the physical world. And it is open, customizable, and commercial ready. So when you show some of the videos, when we're talking about SOP and assembly, understanding the assembly process, all of that was done by fine-tuning 10 videos and giving that to Cosmos Reason and say, here's the SOP, here's a subject matter expert that did it 10 times, here's what I'm looking for. You let me know if this process is being followed, yes or no. And you can do that relatively quickly, like I said, just with the minimum of 10 images. So it really excels around that, and it's actually used in a lot of our blueprints, or can be used on its own, so with video and VSS. So let's talk about visual inspection agents, right? So probably where we say, hey, we're doing AOI now, hey, I got bounding boxes, I'm able to detect errors. How does a visual inspection agent differ? Well, we take things like the vision models, vision foundation models, VLMs. We have things like Tau for post-training. We have Deep Stream Inference Builder that creates those Vision AI pipelines a lot quicker. And now we're able to create these Vision AI agents that are now able to either talk to other agents for reasoning, provide metadata, to maybe root cause analysis agents and that capability. A lot of that's really moving forward. I think everybody's pretty familiar with maybe ResNet 50, YOLO, some of those. But VFMs, available to be fine-tuned through Tau 6, are adding additional capabilities. Image embedding, so foundational backbones, right, that can provide very high level of accuracy. Depth estimation from a single monocular depth, right, through like foundation stereo. Object detection through things like RT data and grounding Dino, and then segmentation as well. The ability to not only tune them, we'll talk about also self-supervised learning. We'll talk about what that means, distill them, and so forth. So we can customize VIA agents with NVIDIA Tau 6. So we can adapt new foundation models. We can pre-train them with advanced techniques like self-supervised learning. We can distill them. That means we took a very large model that was probably trained to look at many things. I told it I only care about 12 things. And so get rid of everything else you don't need to detect anything else besides those 12 things. That's going to make the parameter smaller. It's still going to be as accurate, but it's going to be able to either run faster or run on lower cost hardware. And then we can scale training to production-ready deployment with fine-tuning microservices. Remember, it's never a train once and then deploy, right? It is that self-improving factories, that process drift, it's that always changing capability that sets up that AI flywheel. And so talking about supervised fine-tuning versus self-supervised learning and why that's important for manufacturing. Supervised fine-tuning, everybody kind of knows that, right? I have an annotated data set. Here's the bounding boxes, here's my validation. I give that, right? What does self-supervised learning mean, and how can I take advantage of unlabeled data for domain adaptation? I am the wrong slides. So the self-supervised learning allows me to domain adapt. That means I take a bunch of data that is unannotated, but it's my data. So if I'm looking at transmissions, if I'm looking at gears, if I'm looking at PCBs, right? I just give it a bunch of data and it learns to extract the features. It understands better about what it's looking at. It's not annotated, it can't tell you this is this or not that, but it's gonna be able to tell it. So when I do give it data, and I said, I am looking for a pitting of metal, I am looking for a scratch, I am looking for a dent, I don't have to give it as much data because the annotation is really the costly part of the data curation, right? And I'm still gonna get that really high level of accuracy because that model has been domain adapted, right? It's almost a model that knows specifically, even though it can't tell you it's PCBs, it knows PCBs inside and out. It's sort of self-annotated. And then you take a little bit of data and actually name it and give it the expectations of what you want. Why is reasoning important for visual AI agent, right? So you can look at here, these are solder connections on a PCB, and you have 1 bad and 3 good. But you can tell that the 3 good are different, right? And in a sense, some of that might be, while it's not an error, it still might be indications that my process may be moving toward an error or is not as efficient as it needed. So with spatial reasoning, you can get descriptions of each of the different ones. So even though you're getting that binary go, no-go capability, you're able to get information. And with that information, you can start building a semantic graph of that. So when you do get an error, or as you're looking to create alerts based on this information, you're able to help with root cause analysis and intelligence. So that's really where going beyond sort of what I would say is a data point, right? A bounding box, here's a defect, that's a data point. A go, no go, that's a data point, to actual intelligence, right? Otherwise, right now, this is having to be done by the human operators that may not be efficient in this process, right? They might be like, hey, all of a sudden I got a not okay, but I'm not able to understand why I don't have a not okay. But now you have information here that you can readily tap into that can help with that decision process, even if that might not be the expertise. So that's really where we see reasoning coming into visual inspection. We talked about VFMs and why they're important. We talk about those backbones, and the different models that I talked about. And why it's interesting is because now I can train a singular backbone that can do most of my different tasks. So I can do my data. I don't have to have a different classification model, a different detection, a different segmentation model. I am more efficient in the way I do all those things by training a single backbone, and then I just change the different task heads around those VFMs. And that makes for a more, what I would say, efficient AI kind of flywheel for visual inspection. And then you can see some of the different use cases here, of course, for what it's being used. So we talked about supervised training. So this is the slides that were out of order. So some of the SFT accuracy, the ability to do that is a little bit of a lot of numbers, so I won't go through these. But this is kind of what we're talking about, leveraging Tau as a training toolkit, which really abstracts the training capability, right? We want people to worry about the problem, worry about your data, worry about what you're trying to extract from your data. Don't become a TensorFlow management or don't become a PyTorch management. In a lot of cases, there might be even 2 or 3 forms. So what Tau does is then it abstracts all those training frameworks, the data augmentation, synthetic data generation, the fine-tuning for VLMs, and now provides you a nice toolkit that is scalable, can be deployed on a workstation, can be deployed in Kubernetes capability to build a whole training service around on the cloud to do supervised fine-tuning as long as, if I have the slides right, self-supervised fine-tuning. And this is what we talked about, the domain adaptation. So you see the feature map comparison before and after. So this is where it started to become more adaptive to what it's looking at, even though it doesn't have any labels that has been given. So I have 600 labeled data sets, and I have no SSL. I get 93% accuracy, which is not even close to be what's required for manufacturing. Now, I can sit in a whole bunch of data, something like 700,000 unlabeled data. Of course, is very expensive if I'm going to go and label all those 700,000 images, but I have available to them. So I can first use those unlabeled and just domain adapt my model. And then with the same labeled data set, I can get to that really high accuracy number that's going to make it viable for me to introduce into my manufacturing or my factory floor. We talked about distillation, being able to take a model, so what we would call a teacher model, and distill it down into a student model. So you go from 252 million parameters to, in this case, 600 million parameters. You actually even saw a plus bonus that accuracy went up when I distilled the model smaller. So what does this mean? This means that I can now run on a smaller, lower cost, lower power GPU. It can mean that I can run my pipeline a lot faster. It might mean that I can support more cameras with the same GPU to make that deployment more efficient, right? So I want to take advantage of the latest and greatest architecture models, but if they're very large, it might be cost prohibitive. Well, through distillation, you might be able to mitigate that and actually have a solution that you can deploy at the edge for those far edge, lower cost sensitive or power sensitive, because in the factory floor, a lot of the case active cooling is not possible. So some partner stories. We have Spingens, and they're doing optical inspection, high precision for Cooler Master. Hopefully everybody, if you're into PC gaming or building your own PCs, you should know who Cooler Master is. He's very cool. We have Pegatron, and they achieve 98.8 accuracy on their PCB AOI systems. We have a very cool story, Instrumental. We use them in our own supply chain. So you see here, they actually helped us speed up compute tray assemblies, so the creation of these, by 14 days. So we talk about the complexity of AI infrastructure. If they're here, if you go to their booth, there's a I believe it's a GB200 or a GB300 tray. You can see how complex those systems are and everything that they're doing to help us do that. So it's very much about, we try to eat our own dog food. So we even are deploying these agents and these systems through our partners in our own supply chain. Let's talk about standard operating procedure agents. So we kind of talk about visual inspection, kind of the traditional use case. What about it when there's a human in the loop, when there's a robot in the loop, when I have to look at temporal information across an amount of time? That's where SOP agents come into play. And so it's integrated with Cosmos Reason, direct access for VLM deployment, event reviewer. So it's based off of this video search and summarization blueprint. The blueprints here is a combination of models and other microservices configured to give you a starting point to start building your applications around. So it's not an end solution, but this is a starting point to start building those vision AI agents or the standard operating procedure. And they're targeted, and you can deploy these all the way from Jetson Thor to multi-GPU, multi-cloud, as well as the brand new DGX Spark, if you're lucky enough to have one of those at home. So what is an SOP monitoring agent? So manufacturing is still very much human in the loop. Assembly, maintenance tasks, everything else. As good as we all think we are, sometimes we make mistakes. And so if we can help an operator catch that mistake early, or not enforce, but in a way fortify the training that they have been giving around an assembly process or how to do a job, then that means that I can intersect that error at the genesis of that error rather than 2 or 3 steps down the assembly line where my inspection station may sit, which it might be a lot harder for me to sort of unwrap that onion and go undo that capability. So this is where synthetic data like ISEC and Cosmos can help and come in. We have our Vision AI agents, a combination of VFMs, VLMs, LLMs coming in. And then, of course, our blueprints that we talked about, video search summarization, deep stream for the AI pipeline. And like I said, you have a capability to run these all the way on the far edge on Jetson devices like Thor. So a few examples of creating SOP agents for different ones. So here's DeepHow with Anheuser-Busch. So they did this by taking video of procedures, subject matter experts, and being able to create training assistants and training agents for the new operators. So they were able to reduce training time by 80% and 75% faster maintenance, right? And then probably one of the coolest stories that I heard for DeepHow with one of their other customers is the customer came back and says, it just allowed my guys to have work-life balance. My guy that was a subject matter expert didn't have to be kept getting called in on the weekend to help fix an issue because he was the only one that knows that knowledge. I was able to take his knowledge, and then I was able to essentially create an agent that can feed that knowledge back up. He gets to spend home on the weekends. Operators tend to feel more empowered, right? You want to know you have all the answers. That's not always the truth. Sometimes it's not cool to always be bothering somebody with questions. If I have something on a tablet, on my phone, I can ask questions. You can say, hey, I was either right or I was wrong. Then I feel empowered that I am in control of the process, my job. So actually one of the things when this was rolled out is more of the operators felt they were more safe and secure in their positions because they knew more about how to work the systems without having to rely on others. Siemens, we're the operational industrial co-pilot for operations, transforming shop floor operations, right? So they saw an increase in productivity with agents providing 24/7 critical insights. So they were actually found out a lot of these agents, they use way more on the night shift than they are used on the day shift because, of course, in the night shift, it's a skeleton crew. All the SMEs are not there. But they were able to now take an understanding of how a machine came together. They're able to talk to the PLCs, be able to get the errors. They understand the documentation. They have cameras that are looking at the process of that machine execution. And when something happened, the operator can get insights. This is what this error means. This is how you clear it. This is the issue that happened. Something fell off the suction head. Something got stuck on the conveyor belt. They're able to get those insights right away. So minimizes downtime, allows them to work with the machine a lot better. How do I commission it? How do I turn it back on? How do I change it for different processes? So we actually have a blueprint specifically. It's actually up on GitHub now that allows you to train these agents around Cosmos Reason. So we took that VLM, Cosmos Reason, the components of our VSS blueprint, that fine-tuning microservice from Tau, and now you're able to achieve on the use cases that we've done initially, 98% accuracy with just 10 videos with 5 to 10 minutes of training. So it's not like it's a VLM, you're gonna fine tune it, you're gonna have to be there for 2 days or more to train it. It's actually trained very, very quickly. And then automated training and deployment. So we both have the training and an inference blueprint that you can use to expand or start building your capability. Sub-second learning anomalies, right? That's another thing. This has to run on the edge. It doesn't matter if I record a video and then I found out 2 steps later that they did something wrong, right? You want that feedback to be near real time so the operator can course correct. So an example here is Pegatron. So they saw a 67% reduction in error rates in their laptop with a 7% decrease in labor costs, which was phenomenal. I believe I have a video of this here to show you guys. Oops, go back one. Play. Yep. There we go. So something that is actually very hard to generalize, right? You give a Gen AI model, hey, here's a cable. It probably is understands more of a cable. Hey, here's a socket. Probably has never seen a socket like the one here. And by the way, here's the action to click it in and make sure that it's locked. And it needs to understand all those things. It's not a single image. It's temporal information. It's the ability to take a time motion study or create a time motion study if you wanted to, and be able to say, during these steps, this is what happens, and here's the expectation. And it builds that knowledge graph. It builds that reasoning about what it needs to expect, right? I didn't have to train it on images, then create some additional logic on top of that to essentially build an SOP monitoring capability. Now you're really just going with videos. So a little bit more kind of talking about the building blocks of physical AI. So we talked about computer vision AI resolution. So let's talk about how this really works at a larger scale. We have USD, Omniverse, we have RTX technology, that those new RTX 6000, the pros are great. You can essentially, the 3 computers I talked about, you can do them all in a single GPU. And then we have accelerated computing available everywhere. So that's really what's coming together to build the confluence of technologies for physical AI. And then let's take a look at a video of what happens when this actually all comes together.
Demand for NVIDIA accelerated computing is skyrocketing as the world modernizes traditional data centers into generative AI factories. Foxconn, the world's largest electronics manufacturer, is gearing up to meet this demand by building robotic factories with NVIDIA Omniverse and AI. Factory planners use Omniverse to integrate facility and equipment data from leading industry applications like Siemens Teamcenter X and Autodesk Revit. In the digital twin, they optimize floor layout and line configurations and locate optimal camera placements to monitor future operations with NVIDIA Metropolis-powered Vision AI. Virtual integration saves planners on the enormous cost of physical change orders. During construction, the Foxconn teams use the digital twin as the source of truth to communicate and validate accurate equipment layout. The Omniverse digital twin is also the robot gym, where Foxconn developers train and test NVIDIA Isaac AI applications for robotic perception and manipulation, and Metropolis AI applications for sensor fusion. In Omniverse, Foxconn simulates 2 robot AIs before deploying runtimes to Jetson computers. On the assembly line, they simulate Isaac manipulator libraries and AI models for automated optical inspection for object identification, defect detection, and trajectory planning. To transfer HGX systems to the test pods, they simulate Isaac Perceptor-powered Ferrobot AMRs as they perceive and move about their environment with 3D mapping and reconstruction. With Omniverse, Foxconn builds their robotic factories that orchestrate robots running on NVIDIA Isaac to build NVIDIA AI supercomputers, which in turn train Foxconn's robots.
So, great example. Maybe we're not quite there yet on every aspect, but it's all coming together, right? You saw the ability to digital twin, simulate, create synthetic data generation to train, whether it be your facilities cameras, your inspection, the perception for your robots, That's another visual AI agent, right? It's not just always going to be pre-programmed. Now the ability to key off certain things, go talk to that agent, and then be able to tell the robot, I need you to go pick this up, or this is the location, or I need you to go check this out. And he does his dynamic path planning. It's also going to be very key. So, last slide, a little bit call to actions. There are 2 paths to get started, right? Develop yourself. Use our tools, are the 3 computers, the components within Metropolis that allows you to do that, or engage with our partners. Levitas, Siemens, Instrumental, they're all here, Accenture. Go talk to them, go check out their booth, their capabilities, and leverage the ecosystem. And if you're building your own solution, come find me. I would love for you to be part of our ecosystem. Thank you.
All right, we have time for a couple questions. If anyone has anything for Alvin, looks like there's one in the front. Yeah.
Sorry, where did I miss it?
Right here.
Thank you.
Yeah, thanks for the session. That was great. You mentioned that the inferencing is sub-second. Can you say exactly what portion of the second is it like? Can it run like 10 inferences per second or?
Oh, you're talking about the SOP monitoring agent and the VLM?
Yeah.
That's going to be dependent on the hardware. There's probably some benchmarks I can give you on, but it's all going to, actually, if you look at the documentation for VLM reasoning, that's pretty much.
So we are planning to actually use Tor. If has there been any kind of benchmarking on Tor to see how it will perform, especially for
Yeah, there is. I just don't have the data. In front of me, so, yeah, but there is data there too.
Thank you so much.
Thanks.
Hi, quick question. Does the self-supervised vision fine-tuning degrade the reasoning post-training? Because those seem like 2 different.
No, it's actually 2 different models. Oh, sorry about that. Yeah, so you would potentially do the VFM, so the vision foundation model, and then do the self-supervised learning. So you would domain adapt it, and then potentially you're taking both the image data plus the metadata that you're able to extract with that VFM, and you're giving it to the VLM to do the reasoning part of it itself. So,
Okay, gotcha.
yeah. Thanks. Yeah.
Hey, on the video, the first video you showed like a clean wafer, and then there was something doing some kind of, I guess, anomaly detection on the wafer. Was that zero shot?
That was prompt engineer zero shot.
Okay, and so what model was that using?
I believe that was either NVIDIA or Cosmos Reason.
Okay, NVIDIA or Cosmos Reason. Thank you.
One more.
Thanks.
With latency being critical in this, is it possible, or do you think it's okay to deploy this on the cloud? Or I guess you mentioned putting it on the edge. What?
Yeah, I mean, it depends on what it is. Mostly what I expect is going to happen, you are going to have those critical latency systems that have to be deployed at the far edge, right? You're a bottling plant, you're expecting labels, you're expecting bottles. Those machines move really, really, really fast. So there's no way you can do your inspection agents around that. Now, that doesn't mean that you have that first stage that is able to do it within 120 frames or even more or faster, and that's providing your first line of data or capability. And then you're using something else in the cloud to do additional reasoning or reporting using VLMs. You might even be training in the cloud. When we talk about that self-improving factory or the AI flywheel, you might be taking those new defects or the anomaly detections that you're doing at the far edge at speed and saying, okay, this might be a new anomaly gen or collection, and then sending it up to your training computer, which might be on the cloud, that is then updating your model for the process.
So how are you, there was a picture of Apple Vision Pro. I was just wondering, how is that being used to simulate data, create data, or what was the purpose of Apple Vision Pro?
I don't quite know the specifics around that. I think that was walking through the digital twin using the Apple Vision Pro of the factory. Yep.
All right, that's all the time we have for questions. Let's give a big round of applause for Alvin.
Thank you.